We're going to be looking at linear programming very soon. Before I tell you what linear programming is, we're going to start with a few of the fundamentals that need to be in place in order to carry it out. I don't want you to be distracted and confused by drawing straight lines and inequalities when you're also trying to make sense of the context of a linear programming problem. So other than to tell you that linear programming is about optimization, making something as good as it can be, I'm not going to talk specifically about that in this short video. What I am going to go through is the details of how we sketch straight lines and how we sketch inequalities that are similar to sketching straight lines but with a bit of extra nuance, and then a little bit about how we can investigate the region left behind when we've excluded various regions. So to start with, if you've not yet looked at the straight line graphs worksheet that I've got pictured here, I recommend that you pause and you have a go at that. Hopefully a bit of a reminder how to sketch straight lines. You've done some when you were working on the demand curve work. We have various straight line equations and we're asked to sketch them on a graph. The simplest way to do this with most straight line equations is to figure out where they cross the x-axis and figure out where they cross the y-axis. So look at what happens when x is 0 to find out where they cross the y-axis, and look at what happens when y is 0 to find out where they cross the x-axis. When you've done that, you can come back, unpause the video. I'll show you the solutions on here. They're also included in the document. So these are the straight lines you should have got. You notice hopefully things like with x add y equals 6, the curve crosses at 6 on the y-axis and at 6 on the x-axis. Now I want to look at one other thing just while we're focusing on this line, and this will come in helpful in a moment when we get to the inequalities. If we look at a point that isn't on the line and we try doing x add y, the x coordinate add the y coordinate for that point, let's see what happens. Let's take this point up here. This point, I think we would usually agree to say this would count as above the line. You might think of it as to the right of the line as well. You can imagine it either as being I started here and I've had to move to the right, or maybe I started down here and I'm moving up. Either way, we're not on the line, we're on one particular side of the line. And this point has the coordinates 4, 5. If we try doing x and y using the numbers 4 and 5, we're not going to get 6, because if we got 6 it will be a point on the line. What we get is a number which is larger than 6. So 4 and 5 gives 9, which is bigger than 6. We can do a similar thing for a different point. If we go below the line, or to the left of the line if you like, we can get a point like this one, the point 3, 2. And 3 add 2 is 5, which is less than 6. So the line doesn't just give us a set of all the points where the x and y coordinates add up to 6, but it also in some way separates all the points where the x and y coordinates add up to more than 6 from the points where they add up to less than 6. If you're above the line, your x and y coordinates will add up to at least 6, or more than 6 if you're actually away from the line. If you're on the line or below, then they can never add up to more than 6. They must add up to 6 if you're on the line, or less than 6 if you're below the line. We're going to see more of how that works in the next slide. So here's a typical situation that you might have within the middle of a linear programming problem. We have various things that look a lot like straight line equations, except for the fact that instead of an equals sign, we've got an inequality sign. To keep things straightforward, we've got less than or equal and more than or equal signs. So we're not going to worry too much about the actual line itself, but what we have involved here is a particular side of the line that we care about. So we need to be either on the line or on a particular side of the line. And the way we do this is we start by drawing the line. Now when I say the line, what I mean is the line that you would get if you replaced the greater than or equal to sign with an equals sign. So for instance, this first one, we imagine not the line y equals greater than or equal to 0, because that's not a line, that's a region, but y equals 0. So the sort of the boundary of the region. And that's the first thing we draw on. So that line there is y equals 0. It's a height of 0. Pick any point on the line, the point 0, 0, 3, 0, minus 2, 0. You'll find that every point has one thing in common: the y-coordinate is 0. The next step is to test a point on one side of the line. Now you can test a point on both sides if you like. We can look, for instance, at, I don't know, a point up here. Let's take the point 1, 7. The point 1, 7, does it fit the rule y is greater than or equal to 0? Well, yes, the y-coordinate is 7, and 7 is at least 0, so it fits the rule. So that point works fine. That point is within the region that we're interested in. If I'm telling you that the y-coordinate has to be at least 0, then the point that I've put on the graph would fit. If we tried a different point, like the point -1, -2 down here, we'd find that that one doesn't fit because the y-coordinate of that point is not at least 0. So we've got one point that fits, another point that doesn't fit. And that is enough for us to see what the shaded side of the line should be. In this case, and depending on the situation, this is sometimes done differently, but we're going to shade the region excluded by the inequality. In other words, we're going to scribble out the section which is not allowed, and that will make it easier to see what's left over. And this is how it works. Shade this out, just draw some rough hatching lines. This is fine. As long as it's clear which side of the line you're interested in and which side you're not, then that will be just fine. So we've shaded out the bit that we're not allowed to be in, and we're left with just the region that we are allowed to be in. And you should find that any point within the region above the line here is valid, and any point below the line is not valid because it doesn't satisfy the inequality. In other words, it doesn't fit the rule. We can do a similar thing with the next one. X is greater than or equal to 1. Well, we consider the related line. We think about x equals 1, and we ask ourselves where that would be. Well, if the x-coordinate is 1, that one is a perfectly vertical line. Neither of these are the same sort that you did on the previous sheet. The previous sheet had questions where the straight lines looked a bit more like this one, where there was an x and a y, but these ones at the top, the y equals 0, the x equals 1, are in some ways simpler because they're telling you the x-coordinate is always the same thing. So pick a few points which have an x-coordinate of 1, like the point 1, 5, the point 1, 4, the point 1, 1, all of these various places. They all have an x-coordinate of 1, and therefore they all lie on the line, and that determines the line for us. Then we check each side of the line again. We pick a side and we consider whether or not the point we've chosen satisfies the inequality. Is x greater than or equal to 1 if we're at the point, I don't know, the point 2, 5 for instance. If we consider that point, the x-coordinate is 2, 2 is greater than or equal to 1, is greater than 1. So that satisfies the inequality. That point is within the valid region. But if we pick a different point, for instance, the point -1, 6, we can see that that point does not satisfy the rule. So we're going to shade out whatever's to the left of this line, and that leaves us with just the stuff to the right. Now you can see we've managed to shade out a couple of regions. The point -1, 6 would have been fine as far as the y is greater than or equal to 0 rule is concerned, but it doesn't fit the x is greater than or equal to 1 rule. In fact, the only point we've got so far that fits all of them is the point 2, 5 that I've marked on, plus all the other points that I've not marked, the point 5, 2, the point 3, 4, the point 7, 25, which is not even shown on here. But all of the points where the x-coordinate is at least 1 and simultaneously the y-coordinate is at least 0, they're the region that we have not shaded in at all. Now we get to the next one. And it's important to mention at this point, we're not looking for places that satisfy just one of these inequalities. Every single one of these is an additional requirement that we need to fulfill. Unless every single one of these is valid, then we're not in a valid position on the graph. We're trying to find the points on the graph that satisfy all 4 inequalities that we've been given. So how do we do y is less than or equal to x? Well, again, you draw the line. We draw the line which corresponds to the boundary of this region by ignoring the inequality sign and treating it as if it was just an equals sign. Y equals x. Well, this one's a little more complicated than y equals 0 or x equals 1, but what it's telling you is the y coordinate is the same as the x coordinate. So if the x coordinate was, say, 5, then the y coordinate would be 5. That makes a point on the line. If the x coordinate was 2, the y coordinate would be 2. You can try doing what we usually do for the more complicated lines. For this one, set y equal to 0, then x will be 0. Set x equal to 0, then y will be 0. So we can see that it crosses the x and y axes at the same point, 0, 0. That point on its own wouldn't be enough for you to draw the line, but if you pick a different x or y coordinate, you'll immediately be able to calculate the y or x coordinate. They're always going to be the same. That gives us this line. Then we need to figure out which side of the line we belong on. This is a little more complicated than just we need to be above y equals 0 or we need to be to the right of x equals 1. We're saying y, the y coordinate, has to be less than or equal to the x coordinate. So the height is not a fixed requirement height, it's a height that depends on the x coordinate, how far along you've gone. And this is where it really comes into its own to test various points. We can pick a point like this one, the point 4, 6, and we can try it out. Is it true to say that the y coordinate is less than or equal to the x coordinate? Is 6 less than or equal to 4? Well, if it is, we're in a valid region, but if it isn't, we're not. 6 is not less than or equal to 4. So the side of this line that we need to shade in is that side. Picking a random point has shown us that above the line is somewhere we can't be. If the y coordinate has to be less than or equal to the x coordinate, we're allowed points like, say, the point 6, 2, because the y coordinate of 2 is less than or equal to the x coordinate of 6. But we can't have a point that's as high as the point 6, 7, for instance, because then the y coordinate will be too big. We'll do the last one as well. Remember, the only thing we need to worry about initially is thinking about the boundary line for the region. So we focus on the line that corresponds to the boundary. X add 2y equals 6. And for this one, it might be helpful to imagine what happens when x equals 0 to find out where it crosses the y-axis, and what happens when y equals 0 to find out where it crosses the x-axis. So if we set y equal to 0, we get x equals 6. And if we set x equal to 0, we get 2y equals 6, so y equals 3. And as soon as we've got those 2 points, we can draw our straight line. And now we test. Pick a point. I'm going to use this same point that we've marked on here, the point 6, 2. And at the point 6, 2, we're going to ask ourselves, is it true that x add 2y is less than or equal to 6? Well, at the point 6, 2, x add 2y is going to be 6 add 2 times 2. And we want to know if that's less than or equal to 6. Unfortunately, 6 add 2 times 2 is 10, which is not less than or equal to 6. So we need to exclude that side of the line. At the end of this process, you should find, particularly with a linear programming problem, you'll find you're left with what's called a feasible region. This section in here, which you can see, it's been bounded on all sides by an inequality line. The only section on the graph where every single inequality has been satisfied is within that unshaded region. So that we have a special name for. We call it the feasible region. It's the region that is feasible, just means it's possible, or it's doable. It's allowable according to our rules or our constraints. Another word for these inequalities at the top is the constraints of the problem. There are restrictions that mean you can't have a negative value for y, and you can't ever have a value for x which is below 1, etc., etc. When you incorporate all of those restrictions on these two numbers x and y, you're left with just a few places that x and y could be. X has to be between 1 and 6, but if x is 5, then y cannot be 1 because you'd be outside the feasible region. So the values that x is allowed to be kind of depend on the values y is allowed to be, and vice versa. Depending on x and y, that will determine whether we're in the feasible region or not. And the last bit I want to talk about here is where in the feasible region is x as large as possible. This is going to form an important part of the linear programming process. We're constrained to the feasible region. So imagine you are a blob bouncing around inside the feasible region, and you're trying to find a point where x is as large as possible. Well, what are you going to do? You want your x-coordinate to be as large as possible. You're going to head in the direction of larger x-coordinates. But the further you go, the more you can keep going until you reach a particular point. When you get to that extreme end, the point 60, you've got as far as you can go, and your x-coordinate is as large as possible, and yet you're not allowed to go beyond the feasible region. You can do a similar thing for y. We can say, when is y as small as possible? Well, if you're bouncing around inside this region and you want y to be as small as possible, you're going to move downwards. And when you move downwards far enough, eventually you end up on the bottom. And it's interesting here, but there are various points that would correspond to being the smallest possible y value. In fact, anything from 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, any of those places would be a perfectly valid point. Depending on what x and y are, sometimes they're integers because they correspond to the number of a certain product you produce. But depending on what they are, you could even potentially have fractions in between, the point 1.50 and so on. So those two corners, 1, 0 and 6, 0, correspond to minimum values for y, but also everywhere along that line is also a minimum value for y. What's a little more complicated is this last one here. It's talking about x add 3y. So how can we determine where x add 3y is as large as possible? This one's a little harder because it's not immediately obvious which direction you would go in if you're trying to make x add 3y as large as possible. Well, you want to go to the right because that will make x bigger? Well, yes, but you also want to go up because that will make y bigger. And in fact, y has a larger weighting. It's like 3 times y. So going up 1 unit will increase the size of x add 3y by 3 units. Whereas going to the right 1 unit will only increase the size of x add 3y by 1. Let me show you what I mean. If we start at a point in here, if we start at the point 2, 1, we could move to the right, and 2, 1 becomes 3, 1. Well, that changes the value of x add 3y from being 2 add 3 1s, which is 5, to being 3 add 3 1s, which is 6. Alternatively, we could move upwards, and instead of having 2 add 3 lots of 1, giving us 5, we now have 2 add 3 lots of 2, giving us 8. So it turns out moving upwards is better than moving sideways. But depending on the shape of the graph, it might well be that moving upwards and sideways is possible. If you start at 0, 0, you find that you can move up and that will help, but you can also move sideways and that will help. And maybe you can move sideways enough and up enough to get to a point which is the very best. In this particular case, it turns out that this point at the top is the best place to be. But it can get a bit messy, and the more complicated that term x add 3y ends up being, the harder it is to see whether you should be at one corner or another corner. So there's a really nice method you can apply in this case. It's called tour of the vertices, and because there won't be that many corners to look at, it doesn't usually take very long, and it's a very efficient way to do this process. The extremes, a maximum or a minimum, will always occur at one or more of the vertices, the corners. Like we saw for the yellow one, y as small as possible, there were 2 different corners that were joint best for the y value as small as possible. And that will sometimes be the case. But if there is a point in the feasible region that works, there always will be a point in the feasible region that works, and the corners are the only places you need to look, because you want to be at the extremes. If you're somewhere in the middle, you can always improve by moving left, right, up or down, depending on the function you're trying to optimize. So we would mark on the coordinates of the crossing points. Sometimes that's less obvious than at other times. and we'll talk later about how you can determine where they cross. Sometimes it's pretty clear from the graph, and you'll be able to read off the crossing points directly from the graph you've drawn. At other times, you might need to solve equations using the simultaneous equations solver on your calculator. But once you know the x and y coordinates of all the crossing points, every corner for your region, you can test them all. For x as large as possible, you would just look at the x coordinate and you would immediately see that 6, 0 is the best. For y as small as possible, you would just look at the y coordinate and you would immediately see that 6, 0 and 1, 0 both give the lowest possible y coordinate. They're both joint best. Or you could look at both and calculate x add 3y for each one. If we're at the point 1, 0, x add 3y is going to be 1. 1 add 3 nothings. At the point 1, 1, x add 3y gives 4. At the point 2, 2, x add 3y gives 8, as we saw. And at the point 6, 0, x add 3y gives 6. Having calculated them all, we can see which one is the best. 2, 2 gives a value of 8, therefore that one is the very best. Now you can go back to your straight line graphs booklet and you'll find section B involves linear inequalities. There are some similar questions to the ones we've looked at. I'd recommend you work through these. You try some examples of them. There's a couple of similar questions. So question 1 gives you a few inequalities and you're asked to shade the region excluded by them. And then question 3 asks you to optimize some things. In part C, you're doing a similar thing, you just have some additional questions, so you've got lots of practice you can have on this. Now we're going to talk a little bit about the context of the questions that you'll be dealing with. Linear programming is essentially an optimization process. We're trying to make the best use of the available resources. There will be certain constraints, and your job is to work within the constraints to produce the best possible result. So typical examples of optimization that happen in industries all the time. How much should a games developer charge for a new computer game in order to maximize profit? Bear in mind, this is an interesting one because a computer game, once it's been produced, you could very quickly and easily generate new copies of it for a tiny fraction of the cost that you pass on to the consumer. So the cost of producing a new video game for download is very small compared to the price you might charge. If a video games designer only charges a very small amount, however, it's not going to cover the massive cost of developing and keeping updated the video game as things go by. Burger van. How many burgers and how many hot dogs should a food vendor plan to sell given their different prices and cooking times? There might be a certain amount people are prepared to pay for a burger or a hot dog, and it may be that one or other of them costs more money to the hot dog and burger vendor than the other one. It might take more time and effort to produce. There might be all sorts of different reasons why you can't sell just the one. People want variety, and it's similar with a lot of industries. There are certain products that might not get you a huge amount of profit, but you sell them anyway because people come to your shop for one thing and they stay and buy other things. A car factory can produce a number of different models, each with specific time and material requirements. How many of each type should they build? Just because one particular model of car is more profitable doesn't mean the factory can just make that particular model of car, because there may not be the demand for them. If you've got the capacity to make more, you have lots of different equations to try to balance up and make sense of. Various constraints will be involved, including the cost of the different materials, how long you can spend on each particular machine. And you need to weigh these together, build them into your overall model, and determine exactly how much time you're going to spend making each thing. You can spend longer producing custom furniture, but you'll be able to charge more money for it. So are you going to spend all your time making cheap furniture that you can make quickly, or are you going to spend all your time making bespoke custom furniture that you can sell for a lot of money? Or do you need to come up with some balance between the two to optimize your overall profit? Here's the 3 key elements of linear programming. The first is the variables. These are the values that we're able to change in order to affect the outcome. The second are the constraints. They're the limitations that we have imposed on us by the situation. It might be the time we have available or the materials we're able to use. And then finally, something called the objective function. This is the thing that we want to make as big as possible or as small as possible. We might be minimizing cost or maximizing profit. All the key information we can represent on a graph. The reason it's called linear programming is that in this particular situation, we're dealing with things that connect together in a linear way. They produce straight lines when we draw them on a graph. We use inequalities to show the constraints, and we have a feasible region, which is the region left behind when you've got rid of the inequalities. This particular picture shows the feasible region shaded. In the examples we did previously, we shaded everything else so that the feasible region itself was the only part left uncluttered, if you like, which I think generally works better. But the key idea is the same. You'll see it both ways when you look around at other linear programming resources, so it's worth being aware of the two different conventions. The constraints are represented by straight lines, and they will have an inequality associated with them, so you are only allowed to be on one side or the other of a particular straight line. Within the feasible region, you'll be looking for the key places within it that satisfy certain criteria, but we're looking for the places that have the largest possible or possibly the smallest possible value for the objective function. There will be a specific point. We use the tour of the vertices method, which means we look at every single point in order and we determine which of them gives the best solution. If we have a function that determines the profit for a given value of x and a given value of y, then we want to find the point that has the highest possible profit.